Okay, last video of section 4.3, I promise. This is example number 5b. We're asked to find where the graph of f of x is concave up or concave down. So here's our new function, x squared plus 1 over x squared minus 4, and we want to see where it's concave up and concave down. Concave up and concave down, remember, is our second derivative. So we've got to find our second derivative, find our possible points of inflection, and then do our sign test to see if we're positive or negative in our second derivative. Now, before we start on this one, I have a red flag. I have a red flag because I have a denominator. And when I set that denominator equal to 0, I notice that I have vertical asymptotes at x equals positive and negative 2. So that's the first thing you should always be checking before you start any of these problems. Make sure that there is no issues with your domain. Is there any holes? Is there any vertical asymptotes? Is there anything that's going to cause that denominator to equal 0? So we need to keep that in mind, that we have vertical asymptotes in this graph at positive 2 and negative 2. So don't forget about that. All right, we now have to find the first derivative so that we can eventually find the second derivative. So it looks like this is a quotient rule problem. Pause your video, use your quotient rule, and find me the first derivative, please. All right, I have bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. I'm going to distribute. I'm going to combine like terms and see if you get the same answer as me. I got a final first derivative of negative 10x over x squared minus 4, that quantity squared. Now that I have the first derivative, I need to find the second derivative. So we've got to do another derivative here. It looks like this is a quotient rule and a chain rule. So again, pause your video, use your quotient rule, your chain rule, and let's see if we get the same final answer for our second derivative now. All right, I have the bottom times the derivative of the top minus the top times the derivative of the bottom, which is chain rule, over the bottom squared, so that's where that 4 came in as my new exponent. All right, from here, I'm going to see if I can simplify it a little bit, just like I did in my last problem. Okay, so in this first term, I have a negative 10, and then I have the x squared minus 4 squared. In this second term, I have a 10x, I have a 2, and I have a 2x, which gives me my 40x squared, my positive 40x squared. And then I have that x squared minus 4 that's next to it. Just like we did in the last problem, example number 5a, we want to try to make this second derivative look as nice as possible in a factored, most simplified form so that we can set the numerator equal to 0 and solve it easily, and the denominator equal to 0 and solve it easily, so we can find those possible points of inflection. So looking at the numerator, just like I did in the last problem, can we factor out a GCF? What can we take out of both of these terms? It looks like we can take out a negative 10 and an x squared minus 4. So if I take out a negative 10 and an x squared minus 4, then that would leave me with an x squared minus 4 minus a 4x squared. It would leave me with an x squared minus 4 from this first term and a negative 4x squared for my second term. So simplifying that a little bit more, combining like terms, you should end up with a second derivative of negative 10 times the quantity x squared minus 4 times the quantity negative 3x squared minus 4 all over that denominator. So now that my second derivative is written in most simplified factored form, I should be able to now use it to find my possible points of inflection. I should be able to set the numerator equal to 0 and the denominator equal to 0. So that's what I'm going to do, and I'm going to find my possible points of inflection. Pause the video, do that with me, and make sure you have the same answers as I do. Negative 10 equal to 0 kind of goes away, but when I set my x squared minus 4 equal to 0, I end up getting two possible points of inflection at positive and negative 2. When I set the negative 3x squared minus 4 equal to 0, I ended up square rooting a negative number, which are imaginary numbers, so we're not going to deal with that part. And so over on the denominator, when I set it equal to 0 to figure out where my second derivative does not exist, I ended up getting possible points of inflection at x equals plus or minus 2. So I have the same possible points of inflection for both pieces. And so now that I have those possible points of inflection, I'm going to put that on my sign chart, and I'm going to test values, remember, in my second derivative. If we're talking about concavity, we're worried about our second derivative sign. So I'm going to test a number less than -2, a number in between -2 and 2, and a number greater than 2 in my second derivative. All right, so let's test, I don't know, -3. So over in my second derivative, if I plug in a -3 here, -3 squared is 9. 9 plus 4 is some sort of positive, so I get a positive in this piece. My -10 is over here, times a positive so far. If I plug in a -3 here, -3 squared is 9. 9 times -3 is a negative number. A negative number minus 4 more is another negative number. Hopefully you followed me there. So now I have a negative times a positive, which ends up being a positive at the top, right? If I plug in a -3 to the bottom, -3 squared is 9. 9 minus 4 is 5. 5 to the 4th power is some sort of positive. Positive divided by a positive, I ended up getting a positive in my second derivative. I would like you to pause the video and practice that same idea in the leftover intervals. Pick a number between -2 and 2 and pick a number greater than 2, plug it into your second derivative and see what value you get. I ended up getting negative and then positive. Now, so far all of our examples have been that pattern, but that's just a coincidence, so please don't always think that it's positive, negative, positive. It just happens to be in these examples. And so we have values in my second derivative now, and I can figure out where I'm concave up and concave down. I am concave up. My original function, f of x, I should say, is concave up when my second derivative is positive. That's from -infinity to -2, and then again from 2 to infinity. My f of x, my original function, is concave down from -2 to 2, because that's when my second derivative is negative. So then where do we have points of inflection? Well, remember, we have points of inflection when our second derivative changes signs. So does it look like we have points of inflection at -2 and 2? No, be careful. Do you remember back in our original function, we actually have vertical asymptotes at +2 and -2? Well, if there's vertical asymptotes there at +2 and -2, we can't say that there's points of inflection there because there are no points there to begin with. So that's why we needed to be careful of those red flags at the beginning and remember that all the way through the problem. So as soon as I got to my sign chart, we should be putting some sort of indication on my sign chart that this +2 and -2 are vertical asymptotes, so we don't accidentally call them points of inflection. Because on this graph, there are no points of inflection, because the thing that causes the concavity change is a vertical asymptote, not a point of inflection. My concavity still changes, but I don't have points of inflection because there's vertical asymptotes there. I hope that makes sense. If you guys have any questions on anything in 4.3, please let me know, okay?